My talk is part of a education session on quality control for fMRI. All the presenters here contributed to a special issue on fMRI quality control, and we each analyzed a similar data set and described our quality control methods using data. In my paper and this talk, I'm both going to use examples from that data set and construct out a general framework for how to think about fMRI quality control. And I'll be presenting, a little hint of the stuff in the paper, and I'll also be presenting some other stuff as well. I'll start out by saying I have no disclosures. And I'll start with the take-home messages. In the field, there's been a lot of talk about reproducible and relevant science. And I think what's often neglected in discussions is if you really care about that, it requires knowing your data. So much of these discussions focus on pipelines and sample size, but that does not matter if your data does not measure what you think it measures. And I'll note also that the definition of good data varies with context and application. There's no one answer to what's good data. There's many answers for what's bad data, but not one answer for good data. And quality control protocols are central to this process of knowing your data. Automation is absolutely critical for quality control protocols, but it is insufficient. And training how to do QC, I think, does need a lot more attention. And I hope by the end of this talk you'll realize that, and maybe this whole session if you're participating, that QC is an active area of research and should be even more active. So why focus on quality control now? At least my answer to this is that there are significant changes in the field. There's some good changes. We're getting much larger sample size studies, and a lot of us are sharing our data to use these massive data sets. There's some neutral things. As part of getting bigger studies and sharing data, very often the people who design a study are different from the people who collect the data, might be different from the people who pre-process the data, and might be different from the people who analyze the data. What does that mean? It means that very often people are making assumptions about what happened in the previous phases of the study. And it also becomes an issue because, from my experience at least, teaching what data quality looks like is often done through hands-on practice. There's very few, here's a quality control in fMRI course, there's no quality control in fMRI book. So it's kind of taught hands-on, so if you're not collecting data, you're not learning how to do quality control of data. And I think that's concerning. And I think this has been amplified because we just had a pandemic, and there's an entire cohort of trainees who might have collected data, who collected less or no data. So whatever was hands-on, I think, is now even less done. So what do I mean by there's, context matters and, the importance of QC? I'm going to present a mildly provocative case study. And the reason I'm picking out this one is because probably most people in this room know about the Human Connectome Project. And I've frequently heard people say, we use the gold standard data from the Human Connectome Project. And the truth is there's no such thing as gold standard data. If you look at the completely raw, unprocessed data from the Connectome Project, it doesn't look that great. We have massive distortions. This was a pretty much an arbitrary volunteer I picked out. The brain should be symmetric. You can see it really distorted left and right. You see almost, even though it's high resolution, you see very little gyral and sulcal structure. You see dropout down here, all this messy stuff. And just as a comparison, this is a data set from the Abide. This is one of the data sets used in this Open QC process project, also kind of a random subject. And you can see, even with bigger voxels, you have more temporal structure, and it kind of looks cleaner and less distorted. So you have variation like this. And now you can look at temporal signal to noise, which is kind of a basic measure of the power of data to detect changes. And the top one is that same arbitrary subject from the Connectome Project versus the one from Abide. These were both processed in the same, very, very low way, simple way, which is pretty much just motion correction and measure the standard deviation and the mean. And you'll see that for the Connectome Project, the temporal signal noise on this image per voxel is often under 60 and frequently, especially in central cortex, under 20 or even 10, which is, this is outside the brain. So it's effectively at the noise floor in some points in the brain, compared to the Abide data set, which is well over 100 for most of the brain. So looking at the raw Connectome project data, it actually is highly distorted and has really low TSNR. So, context and applications matters. We all know that there's been a lot of great studies coming out of the Connectome project data. But if you think about what those studies are, they're studies that take those small voxels and average all the voxels in our eye. They're studies that, take the really fast TR and do correlations over large chunks of the time series or GLMs across the whole time, or they're averages across the whole population. If you look at the studies that have had trouble with the HCP, there really aren't that many that actually take advantage of the short TR and smallish voxel size that they collected. And as many people know, it was just shown to be a pretty weak data set for brain-wide association studies where you need really high quality data in each individual. I will note that I am making a broad and not completely fair generalization here. This is their unprocessed data. They've used a lot of things to sort of do left-right flipping, correct distortions, average across time denoising. There's a lot of things that so that the preprocessed data does look much better than this, but you kind of get what you start from. So they started from data that was really distorted and really low TSNR, and if those same processing steps were used on data that was more robust to begin with, maybe there would be different things coming out of that data set. And even that I'm being a little bit broad and unfair, but I just want to, I'm trying to grab people's attention here and say don't look at things like this as nothing really is a gold standard. But I think the real take-home message of this is data quality is really specific to your study's goals, and for the Connectome project, there's some great applications, but just because it's great data for one application doesn't necessarily mean it's great for others. And you really have to think about what data quality metrics are relevant for your application. So approaching QC in general, I think one of the underlying questions to always ask is, will these data have the potential to accurately and effectively answer my scientific question? And especially in the time of data sharing, you do want to ask a little bit more and future questions others might ask. So if you can make your data a bit more robust to other people, all the better. You also want to identify data anomalies or unexpected variations that might skew or hide results and reduce problems through processing or removal. So the one people most talk about is head motion, is something you can say we can censor volumes of high head motion, and if there's a run with a lot of head motion, you can just remove that whole run. But as you'll see in this slide and probably others in the session, that head motion is just one factor to potentially consider. And I think the last thing to remember is all data sets have problems. If you're not checking and looking out for problems, that means you're just missing something and you're going to get misinterpreted results. And if you do check and you do set up a good QC protocol, you're going to have fewer unknown problems. I'm not saying none, because I think we're all human and we're all mistakes, but everything we do to sort of find our mistakes and correct them is going to make the data better, the field more robust and more reliable. And I'll also mention that as I was writing up this review, I came across this general paper on quality control from 1996 that I thought was a good read, so I wanted to highlight to people. And one of the things in that paper which I was thinking about already and I really liked was that you can think about quality control as both intrinsic and contextual measures. Intrinsic means sort of a general measure of good or bad. So TSNR is a general measure of what is your signal quality, and contextual measures are things that depend on your specific application, which I'll be discussing a lot in this talk. So in the paper, I tried to sort of lay out a framework of different stages of the study and what would go in a QC protocol. This is obviously small print, but you can see the table in the appendix of the publication. And I divided different areas of QC into study planning, during acquisition, soon after acquisition, and during processing. And I'll note that it's good to divide this stuff up, but in practice these all interact. So you might be checking something after acquisition and say, oh, we're not getting the data we thought we get, maybe we got to change something, either behavioral, instructions to the volunteers, or with acquisition to fix things later. So these phases do interact. And I'll also note that this table in the paper is questions, it's not a checklist. So these are, sort of a guided list of questions you can ask yourself as you're going through a study to help you think about setting up your own a study-specific quality control protocol. So on that first phase, study planning, I'll also say, like, through the next few slides, I'm going to try and sort of sample a few of the questions I have in that table and with a few examples, but there's a lot more you can read up on as well. So for study planning, I think a big question is what QC measures matter for my study. So coverage, distortion, TSNR. I know some people might say, like, we should get the whole brain all the time. But, if you have a study where you really want a short time scale or, really small voxels, and you really are focused in one area, maybe whole brain isn't the key issue, but other things are. Similarly, there might be some studies where you really want to be as precise in your anatomy as possible, and distortion or distortion correction are critical. And some when you're smoothing your data or averaging across the big population, and a little bit of distortion isn't the end of the world. And again, TSNR, there's less TSNR and more data is the same thing. So you can sort of, do you need to get more data? Do you need better TSNR? Or do you want to improve your study? So there's different ways to balance these out, but you have to decide what's important. So, like, for a clinical study where you think you can get a patient giving you 10 minutes of good data, you want every bit of increase in TSNR you can possibly get. But for a research study where you're planning to put the person in the scanner for 10 hours, TSNR doesn't matter as much. And then with study planning, I think operating procedures are also something that is worth a lot of discussion, thought, because setting things up right from the beginning makes a huge difference. So what are you documenting? What do you check in real time during the scans? And what do you save? What data, and what metadata? And not only just what do you save, how do you save it? Where do you put it? How do you organize it so that it'll be there when you need it? And the last part of study planning is piloting. So you really need to test your quality control measures and test these operating procedures. So the more you've hammered things out in pilot scans, the more likely scans with full sessions with real volunteers will be worthwhile of your time and the volunteers' time. So I'm going to focus most on piloting the study here. I think the most important thing to keep in mind when piloting a study is do not use scanning parameters just because they work for someone else. Just to emphasize, do not use scanning parameters just because they worked for someone else. I have seen this so many times, and I've seen so many people get in trouble with this. And the basic thing is that if you're not an expert in MRI physics, there's things that you just aren't going to consider that will affect data quality. And here is kind of a sketch of just one example. Let's say you're going to do acceleration, and someone gave you a sequence that has a multi-slice factor of 3. And you're both using 3T scanners. It could be the exact same 3T scanner, but in their when they ran it, they used a head coil that had same 9 channels in this imaginary head coil. They had their head coil set up this way so that there were 3 rows, and that can resolve differences in multi-slice of 3. And this one has it set up in 2 rows, and it can't. So if you changed head coils, or a head coil was slightly more tuned to some acceleration parameters than others, everything could be the same, and you're going to get a lot worse data using this head coil than that. So this is just one example, but piloting data is the only way to say, like, does this still work? Does it work with the hardware and things I'm using? And I'll also add that, like, if you're not an expert in MRI physics, there's things you aren't going to consider. And I guarantee that if you are an expert in MRI physics, I'm preaching to the choir right now, because you're going to be collecting pilot data, because experts in MRI physics know how much things vary and know how important it is to collect pilot data. I'll also, put in sort of a side plug on collecting breathing and pulse. It's not, sometimes we talk about using these for denoising, but I think even more important than denoising is it's a confounding factor. Rasmus Byrne and Kevin Murphy published a study a bunch of years ago showing that your breathing rate can change during block designs of a task. I had a bit of a horror story a bunch of years ago where I have this lovely paper I published. I was doing 200 millisecond flickering checkerboards. I had nice activity and aging and variation between populations, and I like that publication. Read it, it's wonderful. But what I also had was the unpublished part of that study. I also was trying to see how things vary with different durations of stimuli. So I presented 3, 6, and 12-second duration flash and checkerboards, and I wanted to see how it varied. The trouble was a non-trivial number of my volunteers just held their breath for the duration of the stimulus. So I was getting 3, 6, and 12-second breath holds. And if you don't know, a breath hold causes a global bold response. So if I didn't collect this respiration data, I would have published some really visually appealing results that would have been wrong. So collecting the data is really what is really, really important. Also with data acquisition, check outputs as soon as possible. This is just one example of the AFNI real-time system, where while we're scanning, we can sort of see the brain and the motion time series and the fMRI time series on the fly. So the scanner's starting, somewhere in the middle they move, and you can see that live and potentially tell the volunteer, you're moving, let's fix it, let's collect that run again. And just in general for that, because you really have to document anything atypical. If there's different ordered runs, bad runs, faulty response, your volunteers seem to be falling asleep, because those are the things that kind of get lost over time, and we really regret if those, if someone, especially if you're passing the data to someone else in the future, not knowing that, the subject fell asleep in run 7 is just giving people noise that they didn't need to see. So the second phase I was talking about is soon after acquisition. And I'm highlighting soon after acquisition because I've definitely seen a few situations where people collect a lot of data and then realize there was a mistake much late, too late to correct it, after collecting, a significant portion of a study. So you should, immediately check, did you store what you plan to store? Is the result quality similar to pilot scans? Does the data, the actual data from your volunteers, does it look, good quality data in brains of interest? And also look for artifacts that could be signs of problems. This was an example that happened at NIH a bunch of years ago, where the data looked pretty much fine if you looked at it in most typical ways. But if you kind of set a correlation seed to like this one area, you kind of saw this big blob of activity. And what it turned out was one of the receiver coils was faulty and sometimes just kind of like flaked out and went back in. So if you look through the whole time series, unless you looked in this one little section, everything looked good, but it was kind of causing a major artifact in the task. And this is something that, once they realized was happening, they sent that head coil back for repairs and fixed it. So you want to, if you're checking for things like this early, you'll notice this and actually be able to fix your hardware and save a whole data set. The other thing you can comment on is with processing is the coverage map. So this is from the data from the OpenQC project. I analyzed a task data set and a rest data set. And these are overlap maps of the voxels that are in all this, in the 30 subjects for the task and 20 subjects for the rest data set. And what you can see is the yellow voxels are the ones that every single subject has, but particularly for the task data, as you get inferior, this black line is where it's less than 30, and then it kind of drops off. So we're missing a good bit of the cerebellum in a bunch of subjects, particularly for these task data, where we've lost a good chunk of the temporal lobe actually completely. And the thing to keep in mind, though, is this might not be a problem. So if this task data was collected with a purpose in mind and it did not involve the inferior temporal lobe, then this is perfectly fine. But if the goal of the study was to investigate something down, in these areas that have bad coverage, then it's a serious issue that you want to correct your field of view as soon as possible. Similarly, this is examples of like things you can look for head motion. These are from the AFNI's quality control reports. This was one of the subjects from the task data set that just had high motion all through the time series. You can see on the raw data quite how extreme the slice artifacts are as the head moved during acquisition. And given how much motion this had, across all these different time points, this data set is very likely to be unusable. And here's another subject from the same data set where data looked pretty good for a bunch of times, and then there was this one period with a lot of motion, the data is really bad, and then it's good again. So potentially, depending how much data you need and what was moved out, this data set's potentially usable with censoring out the bad motion areas. Another output from the AFNI report on the task data set is you can sort of automatically give these pictures of the full statistical map. I still don't actually know what the specific task was, but you can see that the activity kind of is in cortical blobs mostly. It's kind of structured. Another measure is kind of correlation with white matter, which there's no clear good, clear perfect on this, but generally the white matter is correlating. It's not correlating kind of everywhere. It kind of is focal. It's has a bit of structure to it. And here's these same maps for another subject where you can see the activity maps. That same map is kind of all over the place, and the white matter is pretty much globally correlating with all of gray matter and anti-correlated to the ventricles. So whatever is happening, the white matter is a bit messy. And what's interesting about this subject is on a lot of the main measures, it looked okay. There was not that much motion, but if one of the things Daphne reports is how much your head motion correlates with the task. And it turns out in this subject, the head motion was mildly correlated to the task condition, but not the control condition. So there was sort of a head motion artifact on task minus control in these data. Here are some other automated correlation measures that are distributed that come out when you run AFNI. This is for the rest data. It kind of does an automatic correlation to various seeds like the posterior cingulate. And you can see in this first subject, it kind of looks default mode-ish. This is kind of that local correlation like where I showed the receiver coil artifact earlier, and you can see kind of everything is pretty well balanced. And lastly, there are these epivariance scans, which kind of show lines in the data that have high variance, which are sometimes a warning of an underlying issue going on. I'll show a bit more of that in the next slide. So this subject was included. This other subject in the rest data, you can see it's just a little bit more noisy. There's correlations to the ventricles, to the posterior cingulate, more stuff out of the brain. Nothing here that I would say is like absolutely horrible, but it's kind of a warning sign. I will say that when I evaluated this data set, I decided to include this one. If I'll be honest and say, like, if the rest of this data set was a little bit noisy, if the rest of the data was cleaner, I probably would have rejected this subject, but because this was kind of typical for a lot of subjects, I kind of erred on the side of keeping it. And here's a subject that I excluded where we really have no brain structure, a lot of edge artifacts. This local correlation is just, there's something correlating here that has nothing really to do with brain structure at all. So these are kind of 3 examples of how these measures can be used. And for follow-up, this is kind of what I talked about earlier for human interaction. Things vary. So these are 2 examples. The left subject is a subject which had an epi-high variance warning. So I used the instant correlation function in AFNI to look at kind of where that happened. And if I sort of go to that area, what I see is, the correlations to this seed are kind of these weird lines that really aren't cortical. And this is the seed time series at that location, and this is motion. So you can see that it's kind of following a bit of a jump in the motion. So it seems like there's a bit of a motion artifact scattered through this data set. And here's another example of human interaction where just on a visual check, we notice this kind of really weird anatomy of kind of this black line going through the cortex. That might just be the fissure, but it might be the sign of something else going on. So I looked at it both we first started on the epi and it looked weird. We looked at it in the anatomical and it was clearly this is in the fissure, so it was not as concerning. And then we did Instacore. It's primarily correlated within that area. So it's a sign that maybe if I'm doing, reporting signals really close to cerebrospinal fluid, there might be sort of an artifact that flows to the data, but I'm not particularly worried about this for cortical activity. Another thing to examine is alignment. So AFNI reports out these images, which are the red border is the edges of the anatomical scan and the underlay is the functional scan. And this is one example where the alignment is done both for the original data and for if you flip the anatomical left and right. And AFNI did this because it realized they did this on the AFNI team because they realized there was a bunch of data sets where they were seeing flipping and it's really hard to say. So just to give you an example, this is the original orientation that was distributed with the data, and this is the alignment. I would look at this alignment and say, not great, but it's kind of good. It kind of follows the edge. We see a little bit of stuff following here and there. Not the best alignment, but probably good enough. But when you flipped the anatomical image, what you see is it lines up perfectly. So this gyrus kind of follows right along the way. The border is much nicer. Just the contours really match extremely well. So so this is kind of something that Afni automatically flagged, and this really is likely a flipped data set. The really bad thing about flipped data sets, by the way, is we don't know what's correct. So if I got this data set from somewhere else, I don't know if the epi or the anatomical was flipped, which means I can't just flip one and say everything is good. I'd have to go back and decide which of the two was the correct orientation to put it together. And then other things happen. So here's the data set where both the original and the flipped anatomical just do not look good. And the best guess here is that the data was actually distributed with the wrong anatomical image. And speaking of wrong anatomical images, at the beginning I said, assume they're mistakes, and that includes yourself. Everyone makes mistakes, and a good QC process is adding steps to catch your own mistakes. So when the group of us originally processed the data for the Open QC project, I had some terrible alignments. These were the alignments I was getting, and I was just saying, reject, these alignments are terrible, I don't know what's going on. And we ended up going into our scripts, and we realized what happened was in our scripts, we misaligned the anatomicals to the epis, and we were aligning the wrong epis to the anatomicals, or the wrong anatomicals to the epis. If you want to know exactly how we made this mistake, if you look at the GitHub repo in the paper, I've detailed it out in all its mess. But I think I really wanted to share this because I'm up here giving a talk on QC like I'm some sort of expert, but part of being knowledgeable on this is knowing that I make mistakes and everyone else makes mistakes, and it's important to design your processes knowing that mistakes are going to happen. The interesting thing about this is, as I began, quality control research is ongoing. One little interesting side effect of that mistake is all these alignments use some sort of cost function. And these cost functions are relative measures, and they don't really have much meaning. But if you look at them carefully, I noticed that within each study, the values were actually pretty consistent. So in the resting scan, for all the runs I considered good, they were all kind of -4 to 0.5. There were 3 subjects that were the ones that had truly wrong anatomicals, and those were the 3 subjects that had very different cost functions. When I didn't make the mistake, when I corrected my mistake with the matching for the task data set, these are the cost functions. And when I had a bunch of them misaligned by our own processing error, the cost functions were all clustered much higher up. So this points out that for our study design, if we're collecting and compiling these cost functions, they might be a potential flag to automatically look at which data are most likely to have bad alignments or other issues going on. The last thing I'll bring up is, when you're thinking about QC, you should think about it in all steps of the process. So this is another project I've been working on, so TED ANA for multi-echo denoising. And as part of the project, we are outputting this dynamic report to explore the results. And at least for my usage, it's been absolutely critical to use, because just getting the results and not understanding them is not particularly useful. And being able to surf the results and examine them has both highlighted strengths and weaknesses of the method and issues with my own data. So this is just a plug that if you are designing your own methods or even your own scripts, building in ways to check your results or finding things people have done is really important. So to finish up, these are kind of rephrasing of my original take-home messages. A good quality control process is fundamental to reproducible and relevant science. I'd actually go even further and say it's more important than sample size and what method we use to do statistical thresholds, which seems to be where most of the discussion is nowadays. And designing a QC process starts with study planning and includes every step, including, and especially this is true for data collected by others, and documentation is incredibly important. And automation is critical. I showed all these automated outputs from Afni, but the human observations and interpretations are what make things kind of fit together. And especially as we get to bigger end studies, figuring out when that human time is most valuable is an area for discussion and research. As I also mentioned a few times, QC is not just keep versus exclude, it's what can I answer with these data. So I think we need to sort of think beyond, good, bad data and more applications. And as I mentioned at the beginning, there's just really not much discussion on this topic or education. I think it really does need more attention. And there's so much more we can do, as you'll see in this whole session with different approaches. It really is an area that is of active research and really should be more active. Again, this is the paper where I go into some of this more often. That's the link to the Open QC project. And I'll note these represent my own views. Thank you for your time.